Hi everyone. Happy start of the semester. It's great to see so many faces come despite the slow start. Today we're fortunate to have Kaden Hazzard from visiting us from Rice University. A bit of background on Kaden: did his PhD at Cornell, and after completing his postdoc at Gila, he joined Rice as a faculty in 2014, and now he's an associate professor at Rice. Kaden is a recipient of many awards, including the NSF Career Award, and he's also an APS Fellow. And his work is at this interdisciplinary intersection between AMO, condensed matter physics, and quantum information science, where broadly he's interested in emergent phenomena, properties of many of our systems, and how these systems and their properties impact applications in simulators, and sensors, and in quantum information in general. He has done an enormous amount of influential work, especially with neutral atoms and polar molecules. And he was also graciously volunteered his time to also collaborate with people who make fake atoms in the lab. And today he will talk about new forms of particles and maybe jumping ahead ways in which we can see them in the lab. So take it away.
Thank you so much, Andre, and thanks everyone for coming and listening to what I have to say. I'm going to be talking about something that's rather exotic sounding and maybe exotic in practice, which the key message is that I think we all learned that fermions and bosons are supposed to be the only things that nature allows, at least in ordinary three-dimensional space. And my claim is the rather heretical thing that no, in fact, it's possible to have particles that are neither fermions or bosons in three-dimensional space, and this does not violate any of the cherished principles of physics that we all know and love. Now, as Andre said, my real research, or the heart of my research, is actually much more less exotic sounding things. I like to work in quantum simulation and thinking about new phases of matter or how to detect these in an experiment. So if you'd rather hear about that stuff, it's too late. You're stuck here and you can't escape. So, but please come up after the colloquium, and I would be happy to share what's going on that front with any of you. So this is just to get it out of the way, to acknowledge the people who've really done this work. So I have to first and foremost acknowledge Jiwan Wang. He is a former graduate student in my group that's now a postdoc at the Perimeter Institute. And actually, everything I'm going to tell you about was initially his discovery. This just wouldn't have happened without him. It was not my suggestion he go look at this. It was sort of organically grew out of things he was thinking about. And now I have other excellent graduate students here at Rice that are thinking about how can we understand these things better, how can we see them experiment, and both in synthetic matter and in real materials. And we're having a lot of fun with this. And some experiments, which I'll just hint at, are being done in the experimental group of Bryce Gadway at Penn State, along with his fantastic group. And do hope that actually in just a couple months we will have some signatures of these paraparticles as emergent particles in matter. So what are the key takeaways? Oh, sorry, but first, some of the other things I do work on, and just in case anyone's interested and wants to talk about, a lot of things I do are about actually what happens when you put fermions in optical potentials. You can do this in these nano-Kelvin gases, but the point is that they look very much like real solid state systems of electrons moving around in the lattice. And so we're really interested in what happens when you dope Mott insulators or other interesting solid state phases like this. How do holes move? What phase of matter can emerge here, and what can we learn about it from these sorts of experiments? Another direction is sort of using the internal states of these cold atoms to act like an extra dimension of space that you can control. Just at a mathematical level, it's equivalent to having this extra dimension of space. And so with experimental collaborators, they've manipulated systems like this to look at topological edge states and just interesting new physics that wouldn't occur in ordinary materials. And then things like entanglement in solid state systems, and with Andre getting introduced to superconducting circuits and all this fun stuff. So if you'd rather hear about this stuff, please talk to me, and I would love to talk about any of it. Okay, so the main takeaways I want to get are that we're going to study these paraparticles. By paraparticles, I just mean something that's not fermions or bosons, and of a particular type that I'll discuss here. And I want to give you a warning that you may have heard of these things called anyons. these are not, unlike anions, these can persist in 3 dimensions. Anions are another exception, something that's not fermions or bosons, but they can only live in 2 dimensions. So that's really the key distinction here. They are also, and if you've never heard this word before, just ignore what I'm about to say. They're not parafermions. Parafermions are actually something totally different. There's no relation, as far as I know, between these 2 things. And if you've never heard of them before, that's fine. Just pretend you still haven't heard of them. So this is just for the couple of you that may have heard of parafermions, and I don't want to get you confused. So what are the key takeaways? The key takeaways are, as I said, there are these new types of particles. On the one level, they're both consistent with the things that we know physical system must satisfy. Things like locality, that you can't signal faster than the speed of light, and unitarity, that you can't just lose probability amplitude. But also that they can emerge as quasi-particles in real materials. So you have some spin model, or you have a collection of fermions, and when you excite it, those excitations are described as quasi-particles, which can actually be of this paraparticle type. And then other things that are very important, and maybe not so easy to appreciate, or not as obvious to appreciate, are that these models we've constructed that can have paraparticles are exactly solvable. And they're just non-interacting particle models, much like you'd have non-interacting fermions or bosons. And if you're familiar with anions, this known exception in 2D to fermions and bosons, we've never had exactly solvable models of mobile anions before. We've never had a non-interacting theory of anions before. And so even independent of the sort of new type of particle stuff, having these new non-interacting theories actually gives us a lot of purchase on understanding anions in 2 dimensions, or I hope it will. It promises that possibility. And so actually I'm going to spend probably a third of this talk, maybe, I hope it's not unappreciated, is explaining to you why you should care about particle statistics, and explaining why you should care about having non-interacting theories with different types of particle statistics. And I encourage you just to stop me at any point, and I'll be happy to, I'll make sure that we end on time. Or he'll make sure that we end on time. Okay, so let's start. Nature only gives us 2 things, seems to only give us 2 things. Every particle we know, every fundamental particle as well as every emergent particle, is a boson or it's a fermion. Bosons have symmetric wave functions, integer spin. Fermions have anti-symmetric wave functions with half-integer spin. They have very different properties. Bosons like to clump up at the same point in space or in the same momentum mode, whereas the fermions exclude, right? So 2 fermions don't want to sit in the same point in space. We have Pauli exclusion. And this is really crucial to the behavior of sort of everything. So, and maybe in surprising ways, so you can not only for fundamental particles, but for emergent particles. What do I mean by this? If I have a solid, this is a bunch of nuclei that can vibrate around, and the waves of these vibrations can be thought of as particles. These excitations behave like particles called phonons. And it is crucial, if you want to understand the specific heat of a solid or to understand the heat transport properties, to know what are the particle statistics of these phonons, these emergent particles. In fact, I would argue that almost always, if you're thinking about a quantum theory of something, one of your first steps, maybe your first step, is always to identify what is the particle content, and in particular, what types of particles you have, fermion, boson, and something else. And so if you didn't, if you pretended phonons were not bosons, if you pretended they were fermions, you'd get very wrong answers for a lot of things that you care about. Other examples include things like putting exciting a metal. So if you excite a metal, you can get things that are sort of fermionic quasi-particles that move around. This is the basis of something called fermi-liquid theory, extremely successful, describing everything from metals to neutron stars in some cases. And the basis of this, the starting point, is understanding that the fundamental excitations are fermionic. And something like dark matter, it's very important in terms of limits on the masses that you're going to get. Is dark matter composed of bosons or fermions? And this is because it will clump differently in gravitational potentials depending on which case you have. So, okay, hopefully we all understand particle statistics is important for governing the properties of matter, including emergent cases. And just to give you a sort of more concrete example of what I mean by an emergent excitation, as well as a very far-reaching one. Here's an example that's sort of biophysical, so, and I know very little about this, but if we think about some light harvesting complex that appears in, absorbing photons for photosynthesis, there are some chromophores, some molecules, some compounds sitting there. And when it absorbs a photon, it excites some part of those molecules to some excited state. And now what can happen? You can think about that as if you put a particle at that point in space. And now that chromophore can de-excite, and the photon moves to some new site and re-excites a different chromophore. It's like a particle hopping around from point to space. And in fact, you can describe this type of process as bosons tunneling around in a lattice. If you pretended these were fermions, it turns out you get wrong properties. So this is a case even far flung from maybe what we're used to thinking about, where particle statistics can be important in understanding the dynamics of this system. Okay, and so the particle statistics is important. It also gives rise to lots of different phenomena, right? So it's not just we're making these distinctions to classify things, it's that it has important consequences. So the whole structure of the periodic table comes because you can't put two electrons in the same orbital. You have to fill up first a spin up in this orbital, then a spin down, then a spin up in the next orbital, then a spin down. The conductivity of metals would not at all behave in the right way if electrons were bosons. However, you can pair fermions to make a boson, and that's what happens in a superconductor. And since bosons like to clump up, they can sort of all clump up and carry a current in a nice way together. And a vivid example of this is actually with the photons in a laser. And I have this nice laser pointer here. And why do I get such a nice beam? It's because all the photons want to clump up and point in the same momentum state, point in the same color and everything. So all of this range of phenomena and many more rely on these properties. So just summarizing all of that, fermions give rise to lots of properties of matter that we know and love, magnetism, metallicity, all this stuff. Bosons give rise to superfluidity and lasing and all of this. And here's this big conspicuous hole of, what else could there be? And obviously I'm going to suggest that there are other possibilities out there. Paraparticles can emerge as excitations, just like you have these emergent bosonic and fermionic excitations. And there should be some interesting set of new behaviors that are implied by this. Okay. And now I want to motivate not just that particle statistics is interesting, but specifically that non-interacting theories are interesting. And why is this? It's because non-interacting theories are how we can get a handle on understanding interacting theories. So most of the matter around us, when we look around, is interacting. Some of it's very strongly interacting. And how can we possibly understand this? There's no way to just write down an analytic solution to it. You can try to put it on a computer, but the world's largest supercomputers don't solve these types of problems. There's some exponential growth of Hilbert space that prevents this from happening. So how do we understand these? 90% of the time as a theorist, one of my first choices is going to be to use something called mean field theory. Okay. Also, 90% of the time of that, it's going to be my last choice to understand the system. But what is the principle here? Say you have a bunch of electrons orbiting a nucleus. This is a many-body problem if I have a lot of electrons. I can reduce it to a simpler one-body problem by picking, say, this electron and pretending that it feels all of the other electrons just on average. And so on average, they just give some background potential that the electron I picked out lives in. I've turned a complicated interacting problem into a simple one-particle or non-interacting problem. And this is the way, this gives us a great description of most of the properties, the basic properties of the periodic table, why it has the structure it does. And it's not just this one example, there are many examples of how we use non-interacting theories. You don't need to read this equation, but there's something called the beta ansatz that is a technique for solving one-dimensional systems. You write down some variational ansatz and solve for the parameters, but you have to get the structure of this ansatz correct. And in doing this, there's a -1 in there, which you might expect comes from fermionic statistics. And so if you had other types of particle statistics, you might be able to write down new variational wave functions that let us solve much broader class of systems. And it's not just like analytic stuff when you're doing numerics, My group, for example, does a lot of what's called determinantal quantum Monte Carlo. And the way this works is it just randomly samples tens of thousands or hundreds of thousands of non-interacting configurations of your system, and by adding them all together, actually gives you the answer for the interacting system. And this is actually, if you're familiar with like lattice quantum chromodynamics, the calculations used to calculate the mass of a proton from QCD, it's very, very, very similar to this technique. It's acting in the same way. And so these non-interacting theories are very important for building up our understanding of interacting matter. And once again, it suggests that if we had non-interacting theories of a new type, we would be able to understand new classes of matter by not just having mean field reductions to fermions or bosons, but to these new types of particles. Or not doing determinantal quantum Monte Carlo, but some analog of it for these new emergent excitations. And so long term, I think this is where a lot of the impact's going to be. Okay, so that's kind of my motivation for you. Hopefully it sounds interesting. I'm happy to pause and take any questions, but if not, I'm going to tell you why bosons and fermions are it. Okay. So why only bosons and fermions? I think we all know this argument. I think some of us have taught this argument. A wave function for two particles, psi of x1 and x2. We're going to assume these particles are identical. And what does this mean? It means if I exchange the position of the two particles, there is no way that I can experimentally tell. There's no measurement I can do to tell that I exchanged them. So it's almost that the wave function has to be the same after exchange, but the global phase of the wave function doesn't matter. So I can acquire a global phase after I exchange those two particles, x1 and x2. And now I just do that twice, and this tells me that psi of x1, x2 is this phase factor squared, r squared, psi x1, x2. I cancel out the psi x1, x2 on both sides, and this tells me that exchanging twice is the same as not exchanging. R squared is equal to 1. Or in a picture, I will draw a couple pictures like this. I have two particles here, and think about these as sort of world lines that you read with time going vertically. I exchange them once, I exchange them twice. It's the same as doing nothing. There shouldn't be a plus or minus there. I've somehow shown this slide 20 times and still haven't fixed that typo. Ignore the plus or minus there. So plus only. So this looks pretty ironclad. There are more sophisticated versions of this argument because you could ask all kinds of subtle questions about this. There's a famous argument from the 1970s known as the Linus-Meerheim paper, or Linus-Meerheim argument, which connects this to the sort of topology of exchanging things. And at least in 3 dimensions, it boils down to the same conclusion, roughly the same argument. Tells you that you can only get plus or minus 1. So where's the loophole? Okay. The loophole is extremely simple. What if this psi had an internal index? So it carried some extra degree of freedom. And then when you swap the particles, that internal index can change. Okay. And there are lots of ways, so this would be described by a matrix, and there are lots of matrices that don't square to, that square to plus 1, but are not plus or minus 1. And that is effectively where the loophole comes from. So let me just write that out in an equation. So I have psi now has some index, and there are going to be a couple more slides with equations. We're going to be done with them, and I'll talk more physical pictures, but I feel obligated to show you what's actually going on here. So I'm attaching this index to my wave function psi. And this index can change when I exchange the two particles. And that's all this equation is saying. So when I swap xj plus 1 and xj, what happens is that this internal index gets changed by the matrix R. Yeah?
Sorry, does that mean that the particles are no longer identical then?
Perfect. So this is exactly what I was about to say. So it sounds like they're not identical because when I swap them, something changed. So this index has to be not observable. So what I'm going to allow you to do is any observable you can write down in your theory is not allowed to see what this internal index is. I might call it a hidden variable, but this term is so loaded philosophically in physics, I've stopped doing this. But in the literal sense of the term, it's a hidden variable you can't access. But even though you can't directly access it, it changes the properties of your system. Now you could ask, how fishy is this? I'm putting in an index that I can't directly observe, like is this okay? But I mean, we do it all the time. Take a gauge field. You can't measure a gauge field. You have to measure gauge invariant observables. That's totally fine. Take the phase of the wave function. It's a mathematical artifact. It's put in, it's not observable, and you're totally fine with this. And so I'd suggest there's nothing so different here. And certainly at the end of the day, when these emerge as particles and interacting spin systems or something, everything works out. And so it's okay and not just a mathematical artifact in that case. But it's a great question. Okay, now we're not the first people to understand this possibility. Actually, before I tell you about that, let me tell you a little bit that you can't just put any matrix R here. Okay, this R has to satisfy some constraints. And we saw one of them already. If I exchange twice, I need to get the same thing back. R squared had better be 1. And so that's this equation here, which I already drew graphically. There's another equation, which is not important, but I just want to draw it because it's kind of fun to draw. It basically says, look, here are two different ways of permuting these particles, right? That are actually the same way at the end of the day. So I take a red, a black, and a blue particle, and I permute it to blue, black, red. And that's also what I've got on the right. Red, black, blue goes to blue, black, red. But there are two ways I can do this. I can swap the first pair, last pair, and then the first, or I can swap the last, first, and last. And those two had better give the same way because give the same answer because they're the same permutation. So you need to construct these R's to satisfy that identity as well. This is called the Yang-Baxter or constant Yang-Baxter equation. It has nothing to do with 1D physics. If that rings a bell to you, it's something a little bit different. Special case of that. But it turns out there are lots of solutions. Mathematicians have studied these for a long time. It's basically just looking at representations of the permutation group. It's the kind of thing that for, 100 plus years, mathematicians have looked at this kind of thing. So we know lots of solutions to that. And in fact, even the founders of quantum mechanics pondered whether this was a possibility. I've never seen anyone write it down in such a fashion that I just did, but I think this is the kind of thing they had in mind. So for example, Dirac says it was found in the experiment that all atomic particles, fundamental particles, are either fermions or bosons. It is theoretically possible to have particles which are neither. There we go, that's something like our paraparticles. But such particles have never been observed. It is a law of nature that all particles are either bosons or fermions. So he seems to think it's completely theoretically fine that we have these paraparticles. Okay. Same thing with Pauli, says something similar. Only the symmetrical class occurs, that's bosons. Only the anti-symmetrical class occurs, that's fermions. And then the other third logical possibility is this ensemble is a mixture of the symmetry classes. And he says, as we shall see, the first assumption is never realized in nature. Well, that's fine. Those are just empirical claims, nothing about the logical impossibility. So what happened is people kept thinking about this and kept trying to come up with theories of paraparticles that are not fermions and bosons. So for example, Greenberg and Mazaya in 1965 wrote down this idea that maybe quarks and the color degree of freedom that they carry, maybe that's actually something like this internal index of the wave function. That's like this hidden variable, if I may have used the term. And so they wrote down a nice theory of that. It turned out not to be at least the most elegant or correct description of QCD. And to the extent it would be correct, it would be equivalent to just having fermions with our usual theory of QCD. And this was based on a mathematical theory of Herbert Green, where he had written down something like a theory for these other types of identical or indistinguishable particles. Okay. But what happened was people found that these theories people were writing down were actually just fermions and bosons in hiding. They were maybe not obvious at first glance, but when you thought about it, it was fermions or bosons. Which makes you wonder, right? As a scientist, are we just too stupid to come up with something that's actually a paraparticle theory? A lot of smart people thought about this. A lot of people worked hard on this. And these people, were excellent physicists. So even though this possibility was acknowledged, why were we failing at this? It suggests that there's a deeper principle at work that forbids paraparticles. And in the 1970s, such a principle was laid out. So in what's known as DHR theory, or DF theory, this stands for the authors Dupliker, Hagen, Roberts, or Buchholz, Fredenhagen. they sort of constructed some theorems that if you wanted a physical system that satisfied these desirable properties, fermions and bosons were all you had. And the key idea, or at least how it's usually been interpreted in the literature, the key idea is that you want your system to satisfy locality. That you can't signal faster than the speed of light. Put another way, if I perturb here, I can't instantaneously affect something on the moon. Seems like a very reasonable criterion, and people, and their assumptions are related but not quite identical to that notion. And it turns out under these assumptions, you turn the crank on 100 pages of algebraic quantum field theory, and they show that fermions and bosons are the only possibilities. Okay. And so what we're claiming is that this claim is not correct. And it's not that the papers are wrong, it's that this result has been overinterpreted. They actually make a much stronger assumption than locality in these papers. And I'm glad to talk to you about what this assumption actually is. It's very interesting, but it's acknowledged in the first paragraph when you open up these papers. It says in paragraph 1 exactly what their assumption is. And it turns out there are lots of particles compatible, or there could be particles compatible with locality that are not fermions and bosons, and we know lots of particles consistent with locality that violate the assumptions of their system. And so what we show in this paper here is that you can write down a mathematical theory of particles that is completely local and is not fermions and bosons. And then also that it can emerge in these systems. So where it emerges, these are systems that have topological order and long-range entanglement, things that I won't dig too much into. But in some sense, this is the key take-home message. I just want to show you a little bit about what these particles are, what the theory looks like, and where we might go look for them in nature. But this is definitely a good place to pause and see what questions you have.
What do you mean by can do secret communication?
Oh, good. Yeah, so I don't actually talk about this in the talk. I was talking about this with the students earlier, but this is a beautiful thought experiment concocted by Zhuan Wang, the student who invented this stuff. And I'll tell it in the sort of parable, which he would tell much better than I do. But there are two long-lost lovers that the gods have separated because they did something to get cursed. And these lovers are named Alice and Bob. And so they would like to send a message from Alice to Bob or vice versa. So Alice is vanquished to one corner of the universe and Bob to the other. And they can move around, but they're never allowed to get close to each other. Okay, and so maybe let me just draw. There's Alice. Here's Bob. Can't get close to each other, but they should. Oh, you probably can't see this over here. I don't know if you can see it over here anybody. I'll try to help. Okay, so they're far away, can't talk to each other directly. And the gods at all time are monitoring for any communication between them. So they measure here and here. They measure everywhere away from Alice and Bob to see if any messages are being sent. And if they are, I don't know, the punishment for Alice and Bob gets even worse. So not allowed to send any messages. Can Alice and Bob still communicate with each other? So one idea you might try is they can move around, they can exchange positions. So if Bob could drop a note, maybe Alice could come around and pick up that note. But unfortunately, this would be detected, right? If I drop the note and I move, well, you can just measure here and see there's a note lying there. If you had a paraparticle system, it turns out it is possible to share messages between Alice and Bob by permuting their locations and doing measurements just at these locations. And no measurement away from Alice and Bob could tell you that a message had been exchanged or read that message. So it's a secret communication protocol. It's it does not violate locality or anything because the time it takes to exchange their position is longer than the time it would have taken a message to get transmitted through the system. So in that way, locality is not violated. But I do like this thought experiment because it shows something about the tension of locality in parastatistics, that there is some communication while these two folks can never get close together. And he has a paper or two actually on his own that really gives some nice examples of this without the dramatic backstory.
So how does this naively compared to EPR pairs and just them sharing an entangled pair in another reduced density matrix.
So an EPR pair doesn't let you communicate the information without additional,
Yeah, classical.
Exactly. So that's really the difference. It does rely on a pattern of long-range entanglement that's behind all of this, though. So this system does rely on some long-range entanglement.
But it seems to be long-range entanglement is not perturbed by local
That's why the message
local
is.
observers.
Yeah, that's absolutely true. Yeah, well, we can go through some more details maybe after. You're absolutely asking the right questions about this. Yeah, good question. Okay, we'll keep going. So, feel free to stop at any point. So, how are we going to incorporate locality into our theory? And one of the key ideas to keep in mind is that when you're talking about wave functions, talking about locality is hard. This shows the wave function's like a global object. It depends on the positions of all your particles, no matter how far away they are. And now, the nice way to deal with this, and please don't leave, is actually with second quantization. So this is just a way of dealing with particle statistics using operators. And I'm going to show the last equations on the next slide that has this. If you can zone out, and I promise the rest of the talk will be just fine. But since it's what we do in the paper, I feel obligated to show you one slide with some equations. Okay, but locality is easier with second quantization. And here's the reason why. Hopefully this is a very plausible statement that if I have a Hamiltonian that's a sum of terms, okay, so that's this sum of over R of AR here. And those terms commute when they're at different points in space. Then locality is automatically satisfied. You could think, if you want, maybe Heisenberg equations of motion. One of these ARs can only couple to the ARs next to it. So if you want to transmit information, AR talks to the one next to it, talks to the one next to it, talks to the one next to it. This is a very general statement. If you can write down a Hamiltonian that's sum of terms that commute when they're far away, you're fine with locality. You don't have to think anymore. And second quantization gives you an automatic way of doing this. So you might remember you have these creation and annihilation operators, and F dagger and F, for example, and pairs F dagger F always commute with pairs F dagger F that are far away, because the F either commutes or anti-commutes. So you get a +1 or -1. When you do it in pairs, then they commute when they're far away. So anything that's a sum of F dagger Fs or products of F dagger Fs is going to automatically obey locality. And so if we put paraparticles into that same framework, we could write down theories that are guaranteed to be local. And that's exactly what we did. So just to remind you how it works for fermions and bosons, and just take some shut-eye if you don't want to look at all the indices. If I have a psi and a psi dagger, A here is supposed to represent where you are in space, or it's a mode index. It could be a momentum index, for example. I, J, those are maybe an internal index, a spin index. When I exchange where they sit in space, then I get the same thing. So I exchange where they sit in space, and I exchange also the internal index. I get the same answer back unless A is equal to B and I is equal to J. For bosons, the anti-commute, or maybe just writing out explicitly, it's clearer here. Psi A, psi dagger B gives me psi dagger B, psi A, and the IJ on the left gets swapped with the J on the right. I'll give you a nice physical picture of all this in just a second. I just get a + or -1 depending on whether I have bosons or fermions. So it turns out the appropriate way to do second quantization is just like we put in an R in the symmetrization of the wave function, we replace that + or -1 with an R here. So that's the equation. Turns out this slide has everything you need to know about the paraparticle formalism. It has, it's the axioms of the paraparticle formalism. Now when you exchange particles at A and B, positions A and B, so B and A get swapped on the right, the internal index, maybe this hidden index if you'll allow, I and J, gets permuted or rotated into some new K and L state. And whatever state you get is just determined by this 4-index object. And just like our R did before, it has to satisfy some equations. They're completely analogous to the equations we had before, and completely analogous to before. Mathematicians know lots of solutions to these equations. So that's it. You define your commutation relations like this. You have to worry about psi, psi dagger, and psi dagger psi. They all look sort of the same. You just permute the indices around. Those are your commutation relationships. And then to ensure things stay hidden, your observables have to contract over pairs. Just like fermions, you had to have F dagger, F pairs in your observables. Here it's the same thing, but you have to sum over that hidden index. That's the rule of the game, just like only fermion pairs, the fermi operators can only come in pairs. And that's the whole theory for paraparticles. And we are guaranteed to have a local theory. That takes a little bit more work, but you can convince yourself pretty easily that these are in no way equivalent to fermions and bosons. Okay, let me say all of this again, but no more equations. So let me just give you the physical picture of what these are doing. So if I have ordinary fermions or bosons with some internal index, we're going to draw it as a spin, but it could be anything. And I initially start with an upspin on the right and a downspin on the left. I exchange them. What happens to the spins? The spins just follow the particles, right? So if I exchange them an up and a down, we'll just go to down up. Right? The spin just follows the particle. The spin up follows the red trajectory. What can happen for paraparticles is fairly remarkable. So now when I exchange them, they can get rotated into a new state. And I'm just drawing a cartoon of this. Don't take too seriously. They have to point in both to the right, but this is an example of something that could happen. The point is they can get translated to some new state, transformed to some new internal states. And this goes back to the question of the secret communication, or what's the tension with locality. This is very weird. You have two particles that never have to be anywhere near each other. You exchange them, maybe one is sitting here on Earth, the other's on the moon, and now you exchange them without ever letting them come close. And somehow their internal states know to rotate. And since I can't measure the internal state, this ends up not violating locality, and you can prove that from the second quantization. But it does give rise to observably different properties than you would have for a theory that didn't have this property. This is the essence of paraparticles. And there's a beautiful graphical depiction. I just like this. These are like the world lines of particles moving around in 3 dimensions. And the internal state is represented by color, which changes as things get exchanged. And this is just one of those wonderful cases where a graphics artist actually captures a lot of physics correctly in one of these pretty pictures, which doesn't always happen. Okay, what other consequences do they have? I'm not going to talk you through the math, but we've seen that in addition to having different exchange statistics, particles have different exclusion statistics, and paraparticles are the same. They can give rise to novel exclusion statistics as well. There's the whole derivation. But let me just show you the plot of what happens after you do the calculation. This is a plot of, say, the occupation of a mode, the number of particles you put in this, say, momentum state or some energy eigenstate, single particle energy eigenstate, as a function of energy divided by temperature. And for bosons, you know that the occupation diverges as that energy approaches 0. At high temperature, it's just the usual Boltzmann law, Boltzmann occupation. Large epsilon actually is the correct way to think about it here. Fermions are this blue curve where you have a step function at 0 temperature that's smeared out by some amount that's proportional to the temperature, smeared out an energy proportional to the temperature. And like I said, there are lots of different types of paraparticles, different solutions for those R's, and those correspond to 2 examples are shown in the curves that I plotted here, known in evocative terminology is example 3 and 4. We have many other examples as well. And you might wonder, can I just kind of rescale these curves to make it look like fermions and bosons? The answer is no. There's no way to rescale these in any natural way that would do that. Yeah.
Sorry, but so then in the high temperature limit, they also don't obey Boltzmann's resistance. Is that what I'm saying?
So the high temperature, depends what you mean by the high temperature limit. So
would they follow the ideal gas law?
Yeah, I would call that the dilute limit.
Sure.
What high temperature means, you have to be a little careful. So the dilute limit is out here.
Mm-hmm.
And in fact, if you fix the number of species, basically, then they all obey the same Boltzmann law. The reason they don't agree here is simply because there's a different number of internal states for some of these examples. So you could make them match over here, but then they would, like here where I've chosen the normalization so it matches on the left for this orange curve. I could have chosen it to match on the right, but then it would deviate over here. Yeah. But if you have the same number of internal states for the paraparticles and for bosons and fermions, they all follow the same quote high temperature limit, although you notice it's the 0 temperature limit in that plot. It's the low occupation limit. Right. Okay. Yeah, any other questions?
I'm just thinking, it seems like it would be more important to have it line up in the dilute limit. And then the question is, how would they behave in the sort of, in the degenerate limit?
Sure. Yeah, I could actually maybe remake the plot. Maybe that's the more natural way.
Okay.
But
if you did that, are there surprises in the degenerate limit?
They would definitely not agree in this limit. But it's just like a vertical rescaling of this. Right? So you can imagine just shrinking this orange curve by a factor of whatever. So the surprise, maybe actually I can just describe this. So here's the surprise. Say you had particles with two internal states. Yeah. So spin 1/2, but again, it doesn't have to be spin. Then what are the possible states that you get for the fermions? I could have a vacuum state. I'm just thinking one energy level here. I could have two states, spin up or spin down. These are one particle states. Or I could put two particles in a singlet rule, up, down. And those are the only states I have for spin 1/2, non-interacting spin 1/2 fermions. It turns out the simplest case we know of non-interacting paraparticles, or arguably the simplest, looks the same, except it excludes this possibility.
Okay.
That's exactly right. And so this will make, if you match the high temperature limit the same, so they have the same number of internal degrees of freedom, this will get reduced to reflect the fact you can't doubly occupy. So it actually looks much like a model of hardcore interacting particles, but somehow it gives you a non-interacting theory in which you can solve everything, which is quite surprising. Yeah, great. Okay, so for the last part of my talk, I wanted to tell you about where we might actually see these in nature. And this is still very much, a lot of this is an open question, but it's also not something we know nothing about. So the simplest cases we know are realizable in ultra-cold molecule systems and ultra-cold Rydberg atom systems. And the experiments that are ongoing are in the Rydberg atoms. And I will at least gesture towards how they might occur there. So to do this, let me take a step back and remind you, like, how can you have an unusual type of particle statistics emerge? What does this mean? So what I'm going to start with is a system of these spins that can point up or down. These are effectively bosonic. And I say this because flipping a spin here commutes with flipping a spin far away. So these are fundamentally bosonic degrees of freedom. And if I just had a couple spin flips here for many Hamiltonians, you'll see the excitations behave like a bunch of bosons. However, I want to consider the following model. So I want a model where each of these can be an up or down. Each of these particles can be up or down or a superposition of the two. And then there's an interaction between the nearest neighbors that just flip-flops them. So it's what I'm drawing here. It's this flip-flop interaction where if one's up and one's down, it can go to the opposite configuration. And that's it. That's the whole interaction. That's the whole Hamiltonian. This is known as the spin 1/2 XY model for the experts. And this model has, here's a ground state. If I have one excitation, I can instead think about this one particle. Remember, it flip-flops and exchanges with its neighbors. It's like a particle hopping around in a lattice. But remarkably, if I have more than one spin flip, the excitations, the fundamental lowest energy excitations, aren't simple spin flips anymore. They're what we call domain walls. So if I start from an initial state, let me go back. If I start from an initial state where all the spins are out of the border, plus x direction, and now I create a low energy excitation, the lowest possible energy excitation from that, I get a domain wall. So where to the right, all the particles are plus x, to the left, they're all minus x. And maybe it's not too hard to imagine that this excitation now hops back and forth just like a particle. But completely astonishingly, when you make lots of these excitations, they act like a non-interacting gas of fermions. And that's something that's not so easy to see, but it's something that was shown by Jordan and Wigner in the 1920s. And there's a mapping where you can represent creating this domain wall as a fermionic excitation. And so this is the case. You started with a bunch of bosons. It's strongly interacting. It looks complicated. But by some apparent miracle, it's actually non-interacting fermions. And essentially, all I'm going to tell you about paraparticles is there's a completely analogous story in this one-dimensional case, right? All I wanted to say that I was leading to is that there's actually something as simple as you take a 3-level system, where instead of a spin 1/2, you take spin 1, and you put some simple rules for the nearest neighbor interactions. And depending on, remember we had the R's that describe different types of paraparticles, depending on what that R was, you'd get different rules for what those interactions are. But there's something completely analogous to what Jordan Wigner did that shows that this maps not to non-interacting bosons or fermions, but to non-interacting paraparticles in these models. Again, just staring at the Hamiltonian, and these are actually pretty commonly occurring Hamiltonians people have looked at before, you'd never know it's non-interacting anything. It looks like a strongly coupled problem, but when you use a sort of new version of Jordan Wigner we invented, you replace strings with what are called matrix product strings. Okay, it's interesting in its own right, but the point is you can show that it's a bunch of non-interacting paraparticles. And these paraparticles are sorts of domain walls, just like the fermions. And so the experiment to realize this that Bryce has got and is doing measurements in, and as I was commenting, his fiber amplifier broke 2 weeks ago, which has delayed the experiments, but it'll get fixed in a week or two, and then we'll hopefully get some more data. But we take 3 what are called Rydberg states of an atom. So these are just really highly excited electronic states. For example, 42s, 42p, and 43s. And we let them interact. Atoms, when they're really highly excited, are just dipoles. You have a positive nucleus, you have a negative electron, plus, minus, dipole. And the dipole-dipole interaction naturally gives you the following thing. So when I have one particle in 43s and a neighbor in 42p, they can flip-flop, just like that spin 1/2 Hamiltonian I wrote down. And they can also do this if I had 42p and 42s. And that's it. Those are the only terms in the Hamiltonian, and this is exactly the simplest model of paraparticles that we know, non-interacting paraparticles that we know. So I can tell you more, but he's going and looking for signatures where you create a paraparticle excitation on the left, you create one on the right, you collide them against each other, and you can actually see their exchange statistics this way. You should be able to see that they are not interacting and just pass through each other apart from that exchange. And then we're thinking about how to extend this even further. Okay.
Is the reason the 43s and the 42s can't interact because there's no photon?
So exactly. So let's remember selection rules from quantum mechanics. We only allow dipole-allowed transitions because what is the dipole-dipole interaction? It's d dot d over r cubed, and maybe if you're very erudite, you remember the 1 minus 3 cosquared theta, which isn't important for this. But the d dot d, that's a dipole-dipole interaction. So that means particle 1 can only do a dipole-allowed transition, particle 2 can do a dipole-allowed. And so there's no 43s to 42s. You might think that I missed a term, because what if I started 42p for 2 states? Then one should be able to go up and one should be able to go down. And those are both dipole-allowed. But these are not linearly spaced energy levels. So it's very, very far energetically off resonance by factors of 100 or something. And it's totally negligible process. So these are the only resonant processes with non-negligible matrix elements that occur. Yeah. But you do have to choose the Rydberg states carefully. If that had been like some, I couldn't do 42s, 42p, 43p, for example. This would not work out. Okay. So, of course, some of the excitement, I've tried to convince you the non-interacting theory aspect and having non-interacting particles is interesting, but a lot of the excitement is we have some new particles that can only exist in 3D, so it'd be nice to get out of 1D for that purpose. And this is going to be a much slower process, but I have faith we will get there. One way of doing this is to give up on a kind of natural analog, something experimental realization, and let's just program it in a quantum computer. Plus, funders love this stuff these days. So this has been done for non-abelian anyons, which are an analog of these paraparticles in 2D. I can clarify more of the relation between these two, but this has been done for the very similar systems by Quantinuum, Google, Misha Lukin's group in a slightly different way in two-dimensional anionic systems. And the issue is that the Hamiltonians we know right now in 2D, where we know paraparticles emerge, they're exactly solvable, we've concocted them, are just horrible, ugly Hamiltonians that like only a parent could love. So we love them because we invented these things, but they have 8-body interactions, and they're really complicated 8-body interactions, even by the standards of 8-body interactions. These are not the kind of things that are just going to be happening in some material. So it'd be fun to fine-tune something up and make this happen, but it's not very natural. This is not really a limitation of paraparticles. This is a limitation of finding exactly solvable models. It's just hard to write down exactly solvable models for anything. And so what we're trying to do is think about more natural ways of looking at 2 dimensions and 3 dimensions. And to do this, we kind of have to go and advance our techniques. Instead of working with these exactly solvable models, we have to think about how can I take a complicated system that's definitely not exactly solvable, something close to a real material, and still understand what its excitations are. And this is something we do all the time in physics, but we don't have a lot of experience doing this when the excitations are these paraparticles, since no one thought they could occur. So we're building a lot of formalism and a lot of thinking about how to do this. For example, how can I take a real system, pretend it looks like this, map it to, say, a bunch of paraparticles, which are now not going to be non-interacting. It's going to look like a bunch of interacting paraparticles, and then apply some approximate techniques, but ones we relatively trust to understand what is the behavior of this system. And we're trying to get to the point where we can do this in some sort of reliable way. In a few years, I hope, I will have much more concrete examples. Right now, I don't know where it's best to look. I will say that in real materials, there are certain compounds that have one-dimensional chains. This is one of them that I'm drawing. And they're one-dimensional spin chains, which is just like the Rydberg system I showed you. So if you wanted to look for real materials with these spin 1 paraparticles, you might be able to do it. And just yesterday, I was digging through the literature to see, are there any compounds that have these spin 1 chains? And I found one. Well, there's several, but there's one that strontium nickel platinate. I have no idea how you pronounce that, but something like this. So the Hamiltonian looked right, and so I went and saw what did they measure. So they measured the specific heat of the magnetic degrees of freedom as a function of temperature. And I should say they know nothing about paraparticles. Actually, I don't even really know why anyone cares about this compound, but they measured it. And they compared to a theory, if you see this dash dotted line that's kind of escaping to infinity, that's a theory of non-interacting bosons, which would be the naive theory of this compound. And you can see it's great at low temperature, but then is clearly not doing the right thing at high temperature. The experimental data is these open circles. And if I just take the non-interacting paraparticle theory you'd expect to describe this system and put it on top, that's this blue curve, which I'd say does a heck of a job. Now, I would say there are other simple theories that also capture the data, so I don't want to say this is smoking gun evidence for this, but it's clear that it's not described by non-interacting bosonic or fermionic particles, where it clearly is consistent with this idea of paraparticles. And I should be, let me be clear, the way I made this is I literally took a snapshot of their paper, took a snapshot of Mathematica, made them transparent, overlaid them on each other. So, this is just speculating and giving a hint that I don't think it's far-fetched to think that there's some of this stuff out there. Was there a question back here? Yeah.
I'm sorry, what is that red line?
So the red line is actually they have a theory as well, which they call a direct strong coupling expansion. Again, it looks like it's a strongly interacting model, so they had to do something to calculate this kind of numerical. And the reason you can't really see it is because it essentially completely overlaps the non-interacting paraparticle theory. So even ignoring the experimental data, just their theory of this, which they had no idea it was a non-interacting model, is clearly totally reproduced by this non-interacting theory, which I think is pretty cool. Okay, so that's about the end of my talk. And what are the broader implications of all of this? Just to remind you what I said, we have all these phenomena that originate from fermions, from bosons. Now we know there's this other possibility. What originates from it? And we don't really know, right? At the center are these non-interacting theories, but we don't really know the zoo of phenomena it can give rise to, right? So to be more concrete with this, Fermi gases are a starting point for understanding a bunch of fermions in 1D, but the systems don't actually end up as Fermi gases. Once you turn on interactions, they're unstable to things like Luttinger liquids. Or if I think about other phenomena, I can ask what happens as you tunnel fermions through a barrier. And this is a very famous problem known as Kane-Fisher problem. And for paraparticles, what is the analog of the answers to these questions? Any system that's described by these emergent paraparticles may have an analog, a para-Luttinger liquid, something like this. And it would be fascinating to know what happens. Or in higher dimensions, fermions, when I turn on interactions to describe a metal, I get Fermi liquid theory. Is there a para-Fermi liquid theory? We know that superconductors can arise from the attractive interactions making a Fermi liquid unstable. Is there an analog of this? What are para-liquids unstable to? And paranematics and blah, blah, blah. There's all kinds of interesting stuff, even solvable quantum circuits that are related to this. And it's really just early days of trying to understand what this physics of paraparticles may give rise to, what it may be the parent. And so if anyone is just bored and looking for new projects, I think there are plenty of them around and we're working on lots of these. So let me conclude. For a long time it was thought that fermions and bosons were all you could have in 3D. We think now, or we've shown that there are other possibilities. We have these powerful new non-interacting theories, which we did not even have for ordinary anions before. And we think that these can give rise to a new understanding of a lot of interacting matter. And we're working to see as much of this in experiment as we possibly can. Thanks for your attention.
Thanks, Kaden, for the awesome talk.
If I understood correctly what you said at the beginning about Monte Carlo, it is difficult to solve a system of many interacting particles. So instead, you do a Monte Carlo simulation of non-interacting particle, but you do it many times, and then you see what happens most often, and this is your solution for the interacting particles. But when you do these Monte Carlos, it is completely independent of any interaction. So in other words, the outcome is completely independent of the interaction. So if you have electromagnetic or strong interactions, it doesn't matter. It's the same thing. Did I understand it correctly?
So you don't. So when I say you randomly sample the non-interacting configurations, I didn't tell you what distribution you sample with respect to it, but that distribution can depend on the interactions. But it's in a classically tractable way you can do with the Monte Carlo. So it's, if you know the formalism of like a Hubbard-Stratanovich transformation, it's basically based on this. But anyways, there is a prescription for how you can explore this classical probability distribution where each point in that probability distribution is a non-interacting system, and that distribution depends on the interaction type and strength and everything.
Okay.
Mm-hmm.
Are there situations where the paraparticles are like fully distinguishable, so that they don't have to obey any symmetry at all? Or
You mean this internal index? That there's not an internal index?
you know that you have, let's say, some bosonic or fermionic system, and you engineer something, and that let's say the paraparticles or the excitations like are somehow fully distinguishable, that they behave like these, let's say, Boltzmann.
That's a very interesting question, and I'm not sure I want to try to answer it on the spot. In some sense, because you have this internal degree of freedom, they are fully distinguishable if only you could measure that. But I've told you you're not allowed to measure that. But there's a giant subtlety that I just kind of swept under the rug and haven't discussed. So if you took literally what I said, that you have absolutely no access to that internal degree of freedom, it turns out that the theory is secretly equivalent to fermions and bosons. There's something known as super selection sectors. The theory breaks into different sectors, which are uncoupled, and within each of those sectors, which is all you can explore in dynamic evolution, it actually looks like fermions and bosons. So you actually have to get a little bit of handle on that internal degree of freedom. And it turns out it's possible to do that by slightly elaborating the theory that I've drawn on here. So you could put defects in the lattice or other types of particles, but then you can do this. But then in some sense, to the extent that you're accessing that internal index, they actually have become distinguishable particles. But this is a very, very subtle issue because it's not as simple as just saying you can do a local measurement of that index. You kind of have to do non-local things or things that are local in special situations. It's a really interesting question that you could also just ask something like, can I get pure Boltzmann statistics, like distinguishable particle statistics, just the exclusion, the whatever you call it, the mode occupation distribution, if I pick the right R matrix, for example. And I think that's an interesting question.
Yeah, I had a question, which I think is probably related to the last comment you just made. You said during the talk that you want this internal index to be totally impossible to detect, construct operators that distinguish different values of this index. On the other hand, you wrote down an algebra of this creation of annihilation operators where commutators of these fields have some delta ij. So at least formally, I think I can just construct outer products of states with I and j indices that are Hermitian operators that do distinguish. And so, and experimentally that corresponds to some, I don't know, interference measurement or something between.
Yeah, let me just go back to that slide. Show you something I said very, very quickly, which may address this. So the observables you're allowed to write down, but what do I mean by this? Write down, I mean you put it in a Hamiltonian, or these could be measurement operators. They don't have to be Hamiltonians. But anything you write down has to sum over that internal index. And this is what ensures that you can't actually measure the value of that internal index or do an interference measurement that would let you just, somehow get a handle on that internal state. So the outer products of these operators, without this sum, absolutely you could distinguish this index. Unfortunately, your theory would be non-local. It would allow you to signal faster than the speed of light. And it's only by hiding it in this sum that you remain consistent with locality.
Am I allowed to create states by acting on a vacuum with one of those?
Yes, the states are totally fine. The Fock space, in fact, is just spanned by acting with creation operators on all the states.
So then why can't I take a state and rotate it or move it around and then interfere it with another?
Okay, so there are two questions. So one is, can I mathematically create a state by acting this psi dagger on it? Yes. Can I physically create a state that is just psi dagger IA? No, because that's not generated by an operator of this form. Okay. And it turns out this is exactly how it works. Under very special things that require an extension of the theory, you actually can create something like what we've suggested. And in fact, the simplest case, you take a 2D model, turns out at the corners of the model, you can always access this. You can create exactly the states you're looking for.
I can end it with a question. Are there any implications for quantum information? Same way how topological order nanions might also solve for backstream.
Yep. Good. So these states that have paraparticles, if you have emergent paraparticles, it guarantees that your state has topological order, at least if there's a gap, because honestly we don't understand about those systems. But this means a few things. One, it can't be sort of adiabatically deformed to something that's not paraparticle, it's fermions or bosons. And we've looked at the operations that you can do by, say, taking a state where these are far away and you have some quantum information encoded in particle 1 and particle 2, and you could ask, can I do an entangling gate by permuting these? This would be like for the Majoranas, you can do an entangling gate by exchanging them in 2D. And the answer is yes. For the examples we've looked at, I think that the entangling gates you get are what are called Clifford gates, just like for the Majoranas. So they're entangling, but they're classically simulable. So if you wanted to do quantum computation, you have to augment them with some other gates, just like you do with Majoranas. So the story seems very similar. Do I know how general this story is, or how specific it is to just the examples we've looked at? I'm not sure yet. But there's definitely the power to do entangling gates, and they are topologically protected from local noise for precisely the same reason in that secret communication challenge. You can't locally tell what's going on. You'd have to do a non-local string measurement to perturb the quantum information in the state.
The caveat is now that you also do these schemes also in 3D.
Mm-hmm.
Right?
That's the novel thing, right? So in some sense, I'd say there's nothing new here for quantum information, at least in any obvious way. at least in the sense of implementing this in the system and doing transformations, except that you can extend it to 3D. I mean, if we just had paraparticles laying around, sure, it'd be great. It'd be a topologically protected quantum computer. I don't have any sales pitch why it would be better to go build a paraparticle quantum computer than to do it with Majoranas, or to even just do error correction in a digital quantum computer. But intellectually, it's interesting that this is a possibility.
Great. Oh,
So you
yes.
said on one side, if one is not looking at synthesis, that these particles are indistinguishable from fermions and bosons. On the other hand, you get different thermal properties of this. So that means somewhere there you sneak.
I did. Very, very observant. The point is to thermalize, you have to be able to go between these different super selection sectors. And the observables that couple you between those independent sectors somehow access exactly what you're
Well, but that means for the thermalization to be physically possible, those observables should be there.
Yep.
Also without talking about thermal.
But it turns out I can show you that you can add those observables and they're completely compatible with locality still. It's not so simple to do it in the second quantized formalism, although it's possible. But for example, in this spin model example I showed you, all you have to do is add a transverse field. Infinitesimal transverse field should thermalize the system. And it won't perturb the thermodynamic properties. So this gives you a way of breaking that super selection and making it thermalize like you want. And it's because you've secretly got a handle, or not so secretly, you've got a handle on the internal index by adding the transverse field.
But then there should just be local operators that create a little bit of field and measure the internal index. And
That's
so,
what it is, yeah.
Okay, but then you're back to being able to detect it. It's not so it's not only operators at this form that are signals.
Oh, that's right. I didn't. So what I said is, if you only allow operators of this form, or what I should have said, I'm not sure what I actually said. What I should have said, if you allow operators of this form, locality is satisfied. I did not claim those are the absolutely only operators you're allowed. And so there are generalizations of this which are not easy to write down in the second quantization formalism, or not as easy, that allow you to still respect locality, but couple these super selection sectors, make it different, give you some access to that internal index. A simple case is actually related to the fermions. So at least in a 1D chain, you're only allowed for fermions to write down products of F dagger F. You can never have a single F, because these would anti-commute if they're far separated. You would signal faster than the speed of light. But the exception is if you just put one F operator in, say, at the left side of your chain. This doesn't violate locality in any way, and it lets you couple those super selection sectors in that fermion case as well. There's like an analogous structure for the fermions, and this lets you couple those. But it's a quite subtle point. Yeah.
Okay, so maybe that's further discussion for wine and cheese, but let's thank you then again.
Thanks, everybody.